All right, so we're going to go ahead and get started. We'll take a look at where we left off last time with our exit ticket at the end of last Tuesday's class, okay? All right, so last time, where were we? Last time we did a little bit of a review in terms of chapter 6. So we talked about area between curves and how to find that. We set up some diagrams to help keep us aware of when we should use which method. We did something similar for 6.2 where we looked at volume by disk or washer method, okay? And one big takeaway that we had from that is that if we choose to use disk and washer method, then we must draw slices that are perpendicular to our axis of revolution, okay? So we need to draw these slices that are perpendicular to our axis of revolution. And then we took a look at a case where we tried to do that, but we weren't able to use the washer method. And so we introduced this new method called cylindrical shells. And we talked about how we don't mean like a seashell, but we mean more like these Russian nesting dolls, where we have cardboard tubes sort of nested one inside the other, okay? If you haven't checked out that Marcel the Shell video, it might be a good study break. All right, so shell method. The lines that we draw now are going to be parallel to our axis of revolution. And that means that the lines we draw are the height of our shell, okay? So whatever lines we draw, that represents the height of the shell. It does not represent the radius of the shell. And when we took a look at a nice image of what this looks like, all right, we were able to see that we have the height of the shell, we have the radius, and that they're all sort of nested one inside the other. Now again, this chart, I said, would probably be really useful to have on that cheat sheet so that you could think about decision making. How do I know when I'm going to use what? And as you prepare for the exam next week, I would really encourage you to practice the decision making, okay? So really thinking about how do you know when you're going to use what method? It's supposed to be a Y, okay? And we had a chance to do one example here. So we went back to that question that we weren't able to answer. And we talked about how we could use shell method to do that. And then we were able to squeeze in another example where we took a look at shell method. And then for your exit ticket, I said, let's take a look at number 4. And I want you to go ahead and set up number 4, okay? So that's where we're gonna start today. Let's think about how we would set up our own diagram, how we would decide what our bounds are, okay? And whether we're doing dx or dy. And so this question came with all these different diagrams, okay? So when we revolve this around the x-axis, there was no hole, it was a solid shape, okay? It's like a solid funnel. And we were thinking about if we wanted to use shell method and we've identified our axis of revolution, then the lines we draw need to be parallel to that axis of revolution. So these 3 blue lines that I just drew are parallel to the axis of revolution, and they represent not the radius, but they represent the height of the shells, okay? So the tallest shell would actually be right along that axis of revolution, and the shell with the smallest height would be like right here somewhere, okay? So I know that we had the fancy diagrams, but I wanted us to practice drawing this by ourselves. So like, how would we set this up if we were drawing our own diagram? So if we draw an XY axis and we draw in our curve, okay, and we know that this is 0, 2. We know that this is 4, 0 from our graph. And if we drew the reflection after we revolved it, we would end up with something kind of like that. And that's reflected across our axis of revolution. So if the question says use shell method, then you need to show me lines that are parallel to that axis of revolution, right? So if a problem says shell method and you be drawing your lines like that, then I know that you weren't listening, okay? So make sure that you draw lines that represent the method that you're going to use. So we want to draw lines that are parallel to that axis of revolution. And so this one would actually be the height for the shell that's like right here. Okay. And I could maybe pick a different color to draw a different shell. So if I wanted a shorter shell, maybe I have one that's like this. And this height is shorter than the first shell that I drew. Okay. So given our shells, in this case, should we use dy or dx?
dy.
Yeah, we're going to use dy, okay? And one of the ways that we can make that decision is we can look back at the chart that we had and say if we're axis of revolution is the x-axis, then we're going to use dy. Okay, so that's one way. If you're like, I don't really understand how other people are making this decision, write down the chart, follow the rule. Okay, but on a more conceptual level, if we go back to our diagram, what we need to have our dy be is it needs to be the direction in which the radii are growing. So my shells are sort of growing out along the y-axis. So that to me is an indicator that I need dy. So then if we think about our bounds, we need y values from c to d, and then r, h, dy. Now let's keep the 2 pi here, okay? So if I'm looking for my c and d values, I need the smallest y value of my original diagram and the biggest y value of my original diagram, okay? So my smallest y value is at 0, my biggest y value is at 2. So I'm gonna go from 0 to 2. Now I still saw a few people who were like picking x values even though they were using dy. So you really need to make sure that you double check that for yourself. So if you've committed to dy, then everything has to be y's. You don't even need to look at the x-axis. What you need to look at is the y-axis, okay? And on the flip side, if you commit to dx, then everything needs to be with x's. All right. Now, what did I say last time about the radius for our cases, right? Like once we decided that it's going to be dy, the radius is actually an easy thing to fill in.
It would just be the y values?
It would just be the y value, yeah. So making the decision of dx or dy actually gives you a lot of direction on how to get started. And for some reason, some folks like to kind of like skip over that step, like it makes them uncomfortable or whatever. So they're like, well, let me just fill in everything else and then I'll figure out if it's dy. But if you make that decision initially, it helps you find your c and your d, and it helps you find your r. So in this case, our r is going to be a y value, okay? Now, the last thing we need to fill in is our height. Okay, so if I look at this diagram right here, the height of this shell is an x value, okay, because it goes sideways. And it has a curve that defines it on the right-hand side. And then it has a curve that defines it on the left-hand side. So when I'm thinking about my height, I should still think right minus left curve, okay? And some of you, I actually saw this in your setup. And I think that's a really great thing to do, because if you think about it as it's always right minus left and you just have to figure out your right curve and your left curve, I think that makes it a little bit more of a global pattern, okay? So what is the right curve that bounds our cylindrical shells?
Y minus 2 all squared.
Yeah, it's just this function right here, y minus 2 squared. In fact, they even gave it to you in terms of y, like they want you to use shell method based on the setup, okay? So the right curve is the y minus 2 squared. And what is the left curve in this case?
Zero.
It's 0, okay? Now this, do you have to write the 0? No, absolutely not. But if you came across a shape that was bounded by a right and a left curve and one of them wasn't 0, then this might actually be a good habit to set in place, because you're allowing yourself a structure that will work for more than just the kind of problems we're looking at, okay? So our setup was 2 pi 0 to 2 of y times y minus 2 squared dy, okay? So let's talk strategy here. What do I need to do to simplify this in order to be able to take an integral?
Foil it.
Yeah, we need to FOIL it, okay? Now by FOIL, I hope we can all agree that that means we need to square this first, and then after we square it, then we're gonna distribute in that y, okay? So 2 pi, the integral from 0 to 2 of y squared minus 4y plus 4 dy, or 2 pi, the integral from 0 to 2 of y cubed minus 4y squared plus 4y dy. Okay. Now, I just want to clarify one thing. Some of you out there are very much the overachievers, and I surely do appreciate that, okay? Now, if you get to a question that says, set up, but do not solve, it is absolutely fine to leave it here, okay? Or even this one right here. If it says set up, but do not solve, I'm not looking for the exact answer, okay? You don't have to go all the way to like foiling it out. What I'm really looking for is, can you tell me like what's the radius, what's the height, do you have the right dx or dy at the end, do your numbers match? Okay, so there's actually a lot of information I can get from just a setup. However, if the question says solve it, then you do need to solve it, okay? So on your final, you can expect that some of the questions will say solve, but some of them will say set up. So when I'm encouraging you to study, like practice the setup, I'm not just saying that to say that, I'm saying that that will definitely help you be successful on the final next week, okay? All right, so Now let's take our antiderivative. So we've got y to the 4th over 4 minus 4y cubed over 3 plus 2y squared. And I'm going to plug in 2, and I'm going to plug in 0. But I do that visual check, and I know if I plug in 0, the whole last term is going to 0 out. So really, I just need to plug in 2. So 2 pi, let's see, 2 to the 4th is 16. Minus 2 to the 3rd is 8. 8 times 4 is 32. Plus 2 times 4 is 8. So 2 pi, let's see, this is 4 plus 8 gives me 12. And let's put everything over 3. So this gives me 36 minus 32. So I get 4 over 3, which will give me 8 pi over 3. Okay. All right. So lots of information in going over this question. Are there any questions that are coming up for you folks right now? Okay. So what I want to do is, what do I want to do? We're going to go back to example number 2 for a moment, okay? So example number 2, the question said to set up and solve using shell method. And so we drew our axis of revolution, and we drew our lines that were parallel to our axis of revolution. And then we decided it was going to be a dy situation because our shells were growing along the y-axis. So what I'd like us to do right now is to take a look at example 3, which is exactly the same problem. Okay, so it says determine the volume of the solid obtained by rotating the region bounded by these curves and the y-axis about the x-axis. So we have the same axis of revolution. But this time, I want us to use disk and washer method. Okay, so help me get started here. Okay, I know we've been talking about shell this week, but it is important for us to think about how do we go back and forth between these two methods and choose the one that is most efficient for that situation, not just the one that is easiest for us to do, okay? So when we talked about this problem using shell method, we had to draw our lines that were parallel to our axis of revolution. But if the question says use disk and washer method, then we want to draw lines that are perpendicular to our axis of revolution. Okay. If I want to think about sketching in the reflection, we could draw that down here. Okay. So if I revolve this shape, I'm going to get sort of like a rounded bowl situation. Now, is there a hole in this shape or is there not? No. No, there's not. Good. And these blue lines that we drew, they go right down to that axis of revolution. So that's one way that we know there's not a hole. Okay. So if there's not a hole, that means I can use the disk method. And disk method is the one that is pi, the integral of little r squared. Okay. And that just means I don't have to worry about an outer radius and an inner radius because there's no hole, okay? Now, in this case, do I use dx or dy?
dx.
Dx, good, because all of these blue lines are stacking along the x-axis, all right? That means I need an x value for my a and an x value for my b, okay? So let me give you just about a minute or two to finish setting up this integral and then going ahead to get started if you can, okay? So go ahead and set up the integral. What do we need? What formulas do we need? Is there anything we need to rewrite? Okay, so take a moment and do that. All right, who's got an A and B value for us here? What do we have for A and for B?
Uh, 0 and 8.
Perfect. We're gonna pick this 0 because that's an x value and this 8 because that's an x value. Brilliant. 0 to 8. All right. Someone else, what do we have for our radius? What function defines our radius?
The cubed root of x squared.
Yeah, the cube root of x, that is our radius. And we don't even need to rewrite it because it's already in terms of x, okay? So we've got the cube root of x, and then we're going to square it because it's little r squared. Good. Okay, so one of the things that is an important algebra skill is knowing how we write something like that in a way that we can actually see the power. So we've got pi integral from 0 to 8. Now I know that the cube root of x is the same as x to the 1/3. And then I have that squared. And so when I'm combining powers, so I have a power raised to another power, I multiply them. So I end up with x to the 2/3 dx. Okay. All right, so now we've got our power visible, and we can go ahead and take our integral. So we'll have pi. I've got x to the 5/3, and then the reciprocal of that is 3/5. I'm going to plug in 8, and I'm going to plug in 0. All right, let's get these constants out in the front together. So 3 pi over 5. And then I have 8 to the 5/3. And I don't need to plug in 0 because, again, 0 is going to 0 out that whole second term, okay? But I really want to make sure that this kind of simplification is a skill that we feel comfortable with, that we're not immediately just reaching for our calculator, all right? That we know how to solve that kind of, or simplify that kind of expression. So if I were going to simplify that, I would rewrite it as like a radical. So this is really the same as the cube root of 8 to the 5th. Okay. And I might not know what 8 to the 5/3 is, but I sure do know what the cube root of 8 is, and I think we all do as well. So when we take the cube root of this 8, what do we get?
Two.
We get 2. Okay. And if we take the cube root of this one, we'll get 2. And we take the cube root of that one, we'll get 2 and 2 and 2. So really, everything inside that bracket is 2 times 2 times 2 times 2 times 2. Okay, because we used the cube root on every single one of those 8s. And every single one of those cube roots gave us a 2. So now we've got 32. So 32 times 3 gives us 96 pi over 5. Okay. So 96 pi over 5, because I know Tuesday was a long time ago, is the same answer that we got on Tuesday when we did this using shell method, okay? So when you study, I think it would be a good idea to take a look at questions like 2 and 3 side by side. If you look at the practice problems that I put up on Canvas and the video explanation, some of those questions I say, hey, here's one question, but let's answer it using shell method and let's answer it using disk and washer method, okay? The good thing about that is if you can solve it one way, you know what your answer should be. Like I know from the other day, my answer should be 96 pi over 5. So I'm really glad that when I got to the end, I got 96 pi over 5. Okay. What I'd like you to do right now is to go ahead and take a look back at your notes for example 2 and what we just did for example 3, and come up with maybe just like 1 or 2 things that you think makes one of them easier than the other. Okay, so in your perspective, comparing example 2 and 3, what are some things that you think, okay, well, I would choose this method because I think this part of it is easier. Or I would not choose this method because I think this part is harder. Okay, so take a moment and take a look at example 2 versus what we just did for example 3. And let's see if we can come up with just like maybe 2 or 3 things that makes one of them easier than the other. All right. Anyone have any thoughts on what makes example 2 easier or example 3 easier? What are some pros and cons that we see?
With the disk and washer method, we're only using one variable, like r squared.
Mm-hmm.
And then with the shell method, we have to use the radius, right curve minus left curve.
Mm-hmm. Yeah, so there were like 2 terms here that we ended up having to integrate.
Mm-hmm.
Yeah. Okay. I could see that being like, oh, I really only just would rather work with 1, not with 2, so I'm going to pick disk and washer. Okay. What else do people see? What makes one feel a little bit more accessible than the other?
I feel like when you're using the dish or the washer method, when it's like turning in the x-axis, it just immediately tells you that, oh, you're going to be using dx or dy instead of using like the shell method. It's like the opposite, so it might be like confusing a little bit.
Okay, yeah. So like disk and washer, it's kind of like what you see is what you get. So if they're lined up along the x-axis, you know it's going to be dx. Yeah. Okay. One thing that I thought of is with shell method, when I was taking the integral, I ended up with just like power rule, like regular whole number power rule. And so that kind of made it a little bit easier for me. But when I looked at example 3, I had like this fractional power. And so when I have to take the integral of that, that's like there's a chance that I could make a mistake there. Or if I don't know how to solve this part without a calculator, then that might be like another negative for the disk and washer method in this problem. Okay. But I think everyone's kind of got their own strengths. So definitely think about what are your strengths and how do you play to those, but also think about like, how do I make sure I know to set up both types? Okay. Anyone else have anything to add to sort of comparing 2 and 3? Okay. Well, so we started off this morning looking at example 4, okay, and we used shell method for that. And so what I'd like you to do right now is take a few moments to re-look at the same problem using disk and washer method. Okay, so we already know what our answer is going to be. At the end, we better get 8 pi over 3. But the setup is different, the diagram is different, and so I'd like us to take a moment to think about how do we set up this equation for disk and washer method. Okay, so take a few moments to set up what you think it's going to look like. All right, and setup includes a diagram, it includes drawing those lines. Those are all part of the setup. All right, so hopefully we've all got the lines going perpendicular to our axis of revolution, because again, as soon as we commit to using disk and washer, we know the directions of our lines. And then based on these lines stacking along the x-axis, I'm able to say this is going to be dx. So what do we get for our a and b values for this? Because in the last problem, when we set it up for example 4, we used 0 and 2.
0 and 4.
0 and 4, very nice, because 0 is our x value here, whoop, and then 4 is our ending x value. So 0 to 4. Good. Okay. What about our radius? Because I see this, and I'm like, well, I'll just do this. Okay, I've seen students do that before, but what's wrong with that?
Gonna solve for y.
Yeah, we got to solve for y. So you have the right idea here in that that's the function that defines the radius. However, you need this to be in terms of x, okay? So let's take a little sidebar and take x equals y minus 2 squared, and let's solve for x. So first thing I'm going to do, I'm going to square root both sides. And then I'm going to go ahead and add 2. So instead of writing y minus 2 squared, what I should write is square root of x plus 2. All right, are there any questions about how I rewrote that? Are you guys all way ahead of me? All right, so we've got pi, the integral from 0 to 4. My radius is square root of x plus 2 squared dx. All right, quick, someone tell me, what is one wrong way to simplify this expression?
Distributing the power of 2.
Yeah, so if you did this, right, you're like, oh yeah, I'm just going to distribute that square. I get x plus 4. Wow, this problem is so easy. I'll tell you what, if you do that, you're not going to get that 8 pi over 3 at the end, okay? So be really careful about the algebra here. This is not a mistake that we want to make. But what we do want to do is recognize that we're going to need to FOIL here. So I have square root of x plus 2 times square root of x plus 2 dx. Okay. Now, when we FOIL, right, we multiply the first term. So square root of x times square root of x is x. And then some folks, when they get to this stage, they're like, oh, I have to multiply the outer term. They're like, I don't know what that is. And what I would encourage you to do is be brave enough. You've made it all the way through a crazy semester of calculus. Be brave enough to be like, well, I don't know what it is, but I know that's like 2 times square root of x, right? That connection, I know you know how to make. But sometimes we get in our own heads and we're like, that can't be right, so I'm just not going to write anything down, okay? But it is right. 2 times square root of x gives you 2 square root of x. And your inner terms will give you the same thing. Oops. And your last terms multiplied will give you 4. So pi, the integral from 0 to 4 of x, not x squared, x plus 4x to the 1/2. So I did 2 things at the same time. I combined these like terms, but then I also rewrote my square root of x as x to the 1/2 because I know I'm going to need to integrate and I know I want to see the power, so I can use the power rule. Plus 4 dx. Okay. Any questions so far? All right. So seems like we're ready to integrate. X squared over 2 plus, let's take this one step by step. X to the add 1 is 3/2, and the reciprocal of that is 2/3 plus 4x from pi to, nope, from 4 to 0, goodness. All right, so x squared over 2 is already simplified. If we simplify this term, we're going to get plus 8/3. And at the same time, I'm going to move, or not move, I'm going to put the 8 to the 3/2 back into radical form. And then plus 4x. And I'm going to plug in 4. And I'm going to write the 0, but I know I don't need to plug it in. All right, let's plug in our 4, see what we get. Okay. So instead of writing 4 cubed and typing that into the calculator as 64, I wrote it out as 4 times 4 times 4. So I could use that same trick I used in the other problem on how to simplify this without necessarily needing a calculator. But if I take a look at the whole numbers, so this is 8 plus 16. 8 plus 16 gives me 24. Plus 8/3 times square root of 4 is 2 times 2 times 2. So 8. So this gives me pi times 24 plus 64 over 3, which gives me pi times, let's put everything over 3. So 24 times 3 is 272. And when I add those, I get 136 pi over 3. May make a mistake somewhere. I feel like I made like a sign mistake somewhere. There's a downfall to knowing your answer already. I'll give you guys a moment to look that over. Let's see if we can't find that mistake. I think this is right if we set it up this way. Did I copy something wrong? Y minus 2.
I have a question about how we set it up.
Oh yeah, go ahead, sorry.
When we set it up in terms of x, we did y minus 2 squared, which is like a right-facing parabola. But x squared plus 2 is the top half of the parabola, not the bottom half. So
Okay, that's a great point. So we only need the top half because we're, oh, are you saying that this is the bottom half?
yeah, And when you solve the square root of x plus 2, you're getting the top half, which isn't like the curve that we're looking at.
So maybe we needed that negative one, huh? Does that matter after we square it? Yeah, I think that's exactly where that mistake is. Thank you for catching that. So the mistake is that when we take the square root, we have sort of two options. And so what we did the integral of is actually the curve that, the portion of the curve that looks like this, and that's not what we want. We want the portion of the curve that's like down here like this. So you're right, we do need a negative sign in front of that square root of x. And that's going to change a whole bunch of stuff here. Let's see what changes. So I need a negative sign there. I need a negative sign here and a negative sign here. Okay. Now negative square root of x times negative square root of x is x. So that's still fine. But what does change is this plus sign becomes a minus. This plus sign becomes a minus. And that means that I don't have plus 4 square root, I have negative 4 square root of x. Okay, so how does this move through our problem? Negative, 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 negative. Okay, so now we do 72 minus 64, and that will give us our 8 pi over 3. All right, real good catch, thank you.
Wait, I don't understand why we have to look at the bottom portion.
Okay, let me draw a better picture, okay? Let me draw a better picture of that. Where do I have space to draw a better picture? Okay, well, we'll squeeze it in here. So if you go on Desmos and you graph y equals the square root of x plus 2, okay? What you will get is you will get this part of the curve. But the problem that we started with has this. So the square root of x plus 2 is a parabola, like a sideways facing parabola. But we don't want the top half of it, we want like the bottom half. So this curve is defining the top part, whereas the way that we define the bottom half of the parabola is y equals negative square root of x plus 2. And it's not the yellow one we want, but the purple one we want, because if we look back up here, the yellow one would have been like here, and the purple one is the bottom half of that parabola. Does that clarify that a little bit?
Yeah, that makes much more sense. Thank you.
Okay. Yeah. All right. So we've taken a look at a few examples. We've got a few more to take a look at. And so let's take a break right now. It is 10:30. So let's be back at 10:40. And then when we come back, we'll finish up example 6 and 7, which are sort of, again, this idea of shell versus disc and washer. So same problem, but using two different methods. And then we'll finish off with question number 8, which I think will be really helpful in preparing for the final when you're thinking about, like, you've got these graphs and thinking about just how do you set up the integrals for the given shape that you have, and trying all the methods, just like we have in that graphic organizer that we saw at the very beginning of class, okay? So let's pause here. We'll be back here at 10:40, and then we'll take a look at questions 6 and 7 and 8. Handout that we're working on, and we're going to take a look at question number 6, okay? All right, so question number 6. We're going to take this shape that is defined by the curve 1 over x, and we are going to set the bounds at x equals 1/2 and x equals 4 and y equals 0. So we have a fully enclosed shape. And now we're going to take this shape and we're going to rotate it about the y-axis. So our axis of revolution is where this little curly arrow is, and that is our y-axis, all right? So what I'd like you to do is take a moment to go ahead and set up a diagram. How would you draw the reflection part? How would you draw the line to show me that you are using shell method and not a different method? All right, and set up that integral. So let's take a couple moments and set up our graph. We're going to make sure that our integrals are all the same before we go ahead and start solving them, okay? All right, so let's take a look at these diagrams and make sure we've got the right diagram going on. So I have a diagram that is very crooked, but we're gonna make this work. So I've taken the shape that they've given me and I've drawn the reflection across the axis of revolution. And now I know I'm using shell method, so I want to make sure that the lines I draw are parallel to that axis of revolution. So that means like I would have one line here, and that line represents the height of the cylinder. And that goes something kind of like this. And so like this would be one of the shells. I could draw another shell, maybe a shorter one. So maybe I have a line here, and that is the height of that shell. And when I connect the tops to make it a cylinder, I can see that the green cylinder or the green shell is shorter but wider than the pink shell. Okay. All right. So the question, dx or dy?
dx.
I can see that the radius of my shell is going out along the x-axis. So that is the correct reasoning that we're going to use dx, not dy. Okay? Not dy, but dx. All right, let's set up our volume formula. So for shell method, I need a 2 pi, the integral from a to b of r h dx. That's going to give me 2 pi, the integral from, they already gave me my bounds, so I know the bottom bound is 1/2 because that's the x value they want me to start at, and that my top bound is 4 because that's the x value I want to stop counting the radius at. I also know that because I decided dx, I can put an x in for the radius. And for my height, all right, the curve that defines the height is this 1/x. And if you wanted to think about top curve minus bottom curve, you could even do 1/x minus 0. That would be okay. All right. But before we go ahead and solve this, are there any questions on the setup?
Yeah, can you explain where the x and the minus 0 are coming from?
Where this x is coming from?
Correct, yeah.
Okay, and then this 0?
Yeah.
Okay, yeah, for sure. So the x is the radius, all right? So if I look at this diagram, okay, like this shell that they draw in the picture right here, that shell has a radius that is along the x-axis.
Okay.
So that's why the radius is x, because the radius is going to change for all of the different shells, but what stays the same is that they're all defined by the x value.
Okay, now I see.
Okay. And then this 0 at the end is, so let's see, the 1/x is the top curve, yeah, and then the 0 is like the bottom curve, and so we can see that the height of the shell goes from the top curve to the bottom curve.
And that's 0?
Yeah, the bottom one is y equals 0.
All right, now I'm with you. Thank you.
Cool. Okay, any other questions about the setup? Okay, so let's see what we have once we simplify. 2 pi, the integral from 1/2 to 4 of x times 1/x dx, or 2 pi, the integral from 1/2 to 4 of 1 dx. Well, even though I've got a fraction in my bound, this is like one of the easiest integrals that we've seen, right? We don't even have any x's in it, so the integral of 1 is just x, and I'm going to plug in 4, and I'm going to plug in 1/2. And so I'll plug in 2 pi, 4 minus 1/2, and this will give me 2 pi of 7/2, and these two cancel out, and I get a volume of 7 pi. Okay. All right. So now that we know our answer for this, let's go ahead and take a look at question number 7, which is the same exact problem, except that we want to use disk and washer method. Okay. So we know that our answer is going to be 7 pi. We hope that Judy doesn't make any more mistakes like she did in the last problem. All right, but the way we set this up, we drew our axis of revolution, we drew the lines parallel to that, and we knew that those lines represented the height of the shell. But in example 7, since we're using disk and washer method, your diagram should look different and your integral should look different. All right, so I'll give you a few moments to set this one up. Draw your diagram. Make sure you clearly communicate with me in the diagram that you're using the disk and washer method by the way that you draw your lines. And then go ahead and see if you can set up an integral that represents this curve. All right, so we've got a diagram here, all right, and I'm actually going to add in some of the coordinates of the points that we have here, okay? So for example, this point up here has an x value of 1/2 and a y value of 2. And this point down here has an x value of 4 and a y value of 1/4. And I get the y values just by plugging it into this equation right here, okay? All right, so if I want to draw the slices on my diagram, then if I'm committing to disk and washer method, these slices better be perpendicular to my axis of revolution. Meaning this would be one slice, right? This would be another slice. And there's an infinite number of other slices. Those are just two representative ones. Now, with the two slices that I've drawn already, let me see if you can answer a few questions. So my first question is, does this shape have a hole, or is it solid? Okay, so are we using disk method or are we using washer method?
Washer.
Yeah, we're gonna use washer, right? Those pink lines didn't even come close to touching our axis of revolution. So there's clearly a hole in the middle here, okay? So we know that we want to use washer. Now, given the way the lines are drawn, should we use dx or should we use dy?
dy.
Yeah, we sure are going to use dy. Okay, because again, these lines are stacking up the y-axis. All right. Now, some of you might be like, I don't know why she sort of draws these random lines, and like, how does she know where to put the lines? And the thing is, it doesn't really matter where I put the line as long as I sort of scan the whole diagram. So these two pink lines that I drew so far, do these pink lines have the same left curve and the same right curve?
Yes.
Yeah, they do, right? So remember this color coding, I can't ever remember what colors I've used. All right, so let's say that y equals 1 over x is this seafoam green color, okay? And then that would be my right curve, and my left curve would be like this purpley kind of color. So the two pink lines I drew have the same right curve and the same left curve. Well, that's good, because when we set up our integrals, we want to make sure that they have the same left and right curve so we can use just one equation, okay? So does this pink line still have the same left and right curve as the other two?
Yes.
Yeah, okay. However, there's always a however. What about this guy down here?
No, it's different.
Yeah, so I would need a third color, like not used yet today, orange. This, the last pink line that I drew, has a different right curve than a left curve. So what that means is I can't use one integral for this one. I'm going to need to set up two. Okay. So here's what we're going to do. We're going to take, let's see if this works. So we're going to take everything below this orange line, and we're going to call that region 1. And then we're going to take everything above that orange line, like this part, and call it region 2. Okay. So our volume altogether is going to be the volume we get from region 1 plus the volume that we get from region 2. So let's see what we get as a setup for each region. So we're going to need 2 different integrals. But what is going to be the same is I am going to need the washer formula, and I'm going to need dy for both of them. So for region 1, I would say that I've got pi, the integral from the smallest y value is 0. What's the highest y value in region 1?
4.
2.
Sorry, 2. Yeah.
Yeah, highest y value, right? So the highest y value is actually 1/4. That's like this corner right here. So the bound, the top bound for the volume for region 1 is 1/4. Now, if I need to do right curve minus left curve, I'm going to need to do the big radius squared minus the little radius squared dy. Okay. Plus the area for region, or the volume for region 2 is going to be pi, the integral from the smallest y value in region 2 is 1/4. So like right at 1/4 it changes. And then the highest y value in region 2 is 2. And because it's washer, I'm going to need a big R squared minus little r squared dy. Okay, any questions so far? Okay. So what color is the curve that is the big R for region 1?
It's like tan.
Yeah, like that tan orangey color. And so that curve is x equals 4. So all I need for that is 4 goes in for my big R squared. Minus, what color is the inner radius curve for region 1?
Purple.
It's purple, yeah. So that purple one, and what's the equation of that purple line?
X equals 1/2.
X equals 1/2. So that's what we're going to put in for our little r. Okay. Plus the volume for region 2. So pi, the integral from 1/4 to 2. The outer radius changes for this one. It's not going to be the tan orange one. It's going to be like that seafoam green one. So I need to have the function defined that way, which is not going to be y equals 1 over x, but I actually need to get x by itself. And when I do that, it's going to be 1 over y squared. Minus the inner curve, the inner radius actually stays the same for this one. So minus 1/2 squared dy. Okay. Questions about this setup? Okay. So before we start solving this, let's take a look back at example 6. I mean, in the time that we took to set that up, we solved this question. We like set it up, we solved it, we were done. Right? So the point of this is to say that, yeah, disk and washer method, I think, is where we start to learn how to visualize things. But sometimes it is beneficial to know a different way, because if I were given the choice, so let's say example 6 just said, determine the volume, use any method that you want. I would start with both diagrams. I would start with a shell diagram like I did here, and I would start with the washer diagram. And I would use my diagram to think, how many integrals am I going to need? Because if the answer is more than 1, probably pick the other way. So I would have looked at my washer setup and been like, I don't feel like adding 2 different integrals together. So I'm not going to choose this method. Instead, I will think about how I can use one method or one integral setup to get to my answer, okay? So we know that the answer for example 6 is 7 pi, all right? So on your own time, feel free to confirm that your answer from example 7 is also 7 pi. But I did want to talk through this setup and just have you understand that, like, yeah, disk and washer method, sometimes disk method is way easier, but on the other side of that reasoning, sometimes shell method is easier, okay? So definitely a tool worth investing in. All right. So let's finish here with example number 8. All right, I'll give you a moment to read that. All right, so we're setting up integrals to determine the volume of a solid obtained by rotating the region bounded by these 2 curves about a variety of axes. So we're gonna look at what it's like when I revolve it around the x-axis and the setup using disk and washer method. But we're also going to look at what happens when we revolve it around the x-axis and we change the method to shell method. Then we're going to look at what happens when I revolve it around the y-axis using disk and washer method, and then around the same axis, the y-axis, but using shell method. Okay, so we're not going to be solving all of these. We're going to be setting them up. And setting them up means drawing a diagram, having your diagram match your integral, and you don't need to simplify that much of your integral, okay? So take a moment. I'd like you to sketch the graphs of y equals x and y equals x cubed on the same graph. And then I want you to find the intersection points algebraically, right? So that's when we set the 2 equations equal to each other and we find out where they cross or where they're equal. So take a moment to sketch those graphs, find the intersection points, and then we'll talk about our setup and how the diagrams change for parts A, B, C, D below. All right. So hopefully you have a graph that looks similar to what I have here, okay? So I've made the linear one, y equals 4x in the green curve, or the green line rather, and the cubic one, y equals x cubed, is the purple one. Now you'll notice from this that there are two different regions, and so for the sake of this problem, we're going to choose the region in the first quadrant, okay? So this is going to be the region that we look at being revolved around different axes. Now that's not uncommon, where you might get a graph that meets in more than one quadrant, but then the problem will say, take the region in the first quadrant and only work with that one, okay? So I know that these directions were not very clear, but on an exam, I would make sure to be clear about that. And in a lot of textbooks, make sure you read the problem thoroughly. They'll usually tell you where that region is if there's more than one, okay? Are there any questions about sketching the graph for this? Okay. So then let's find our intersection points algebraically. So I can say that 4x equals x cubed. And anytime I see some sort of polynomial, I really want to think, move everything to one side, set it equal to 0, and factor. Okay, so I'm going to move this 4x to the other side. All right, and I'm going to look to factor this. And I'm going to look to factor this again. Okay. So what that means is there are 3 intersection points. One of them, the functions cross at x equals 0. Another intersection point is at x equals -2. And the third intersection point is x equals +2. Okay. So what you want to make sure you do is pick the right bounds for the region that you're interested in. So because I'm only looking in the first quadrant, I don't want the one where it's x equals -2, okay? Because that's like this point down here, and that's not bounding the region I want. So instead, I'm going to choose x equals 0 and x equals 2 as my bounds, all right? So this right here is 0, and the second place they cross is 2. All right, are there any questions about sketching the graph or finding the intersection points algebraically? Okay. So now let's think about how we can draw these diagrams if we revolve our region about the x-axis. So let's start with parts A and B, okay? I'm going to go ahead and just draw the first quadrant and the fourth quadrant. And so I know I have this green linear function, and I have this cubic down here. Kind of looks like a banana, and they stop at 2. And then my reflection would kind of look something like this. Okay. And I could draw the same diagram for using the shell method, but if I wanted to look at that disc and washer method, and I'm revolving it around the x-axis, I need to draw my lines this way. Okay. And so if I set up my volume formula, I know I'm going to have a hole in the middle, so I need washer method. And because these pink lines are stacking along the x-axis, I want to choose dx. And so I'm going to get pi, the integral from 0 to 2 of 4x squared minus x cubed squared dx. Okay? So this is my big R, and this is my little r. So the green one that is further away from the axis of revolution is my big R. And the purple one, which is closer to my axis of revolution, is my little r. Okay. Any questions about part A? Okay. So let's take a look at how this will be similar or different for shell method. So I'm still going to draw the same setup. Okay, maybe I'll space it out a little bit better this time. So we've got our linear function, and we've got our cubic function, and I know that we're stopping at 2, and the reflection is going to look something kind of like this. All right, so the pictures in the general sense shouldn't be that different, but I should not see pink lines that are perpendicular this time to my axis of revolution. I should see pink lines that are parallel to my axis of revolution. And when I think about setting up my volume formula here, so I know I'm going to need shell because they told me, and I know I'm going to need dy because these lines are stacking up that y-axis. And so I'm going to get volume equals 2 pi, the integral from 0 to, what is our top bound for the y value?
8.
8.
It's 8. Yeah, how did you get 8?
Plug 2 into each equation.
Yeah, if you plug 2 into any of the equations, you should get 8. So like 4 times 2 will give you 8, or 2 cubed will give you 8, all right? So it wasn't a number that was given. And I think sometimes we like panic a little bit and we're like, I don't know, I'm just gonna pick from the numbers I have been given. But the reality is sometimes we need to do that extra layer of work to make sure we have the right number, okay? So 2 pi, the integral from 0 to 8. My radius is going to be y because I chose dy. And the height is going to be a right minus left situation. So my right is going to be the cube root of y. And the left curve is going to be y over 4 dy. Okay? So this was my right curve minus my left curve, and this y is my radius. All right. So we've taken a problem and we've identified our region and we've set it up using 2 different methods. But no matter which method we pick, we should get the same answer for A and for B. Okay. Now, based off of what we have right here, I hope we're all thinking, that disk and washer method looks a little bit easier than our shell method. right? I mean, you could certainly choose shell method. I don't think it's that much harder, but you end up with fractions in the exponents. You end up with fractions in general. So maybe that's one that if you're not as confident on those skills, that maybe you stick with the disc and washer method for this setup, okay? All right, so I think we're actually gonna finish a little early today. What I would like you guys to do for this exit ticket is I'd like you to do what we just did for A and B, but I want you to do that for C and D. So we're changing it so that now we have a y-axis of revolution. So we have a vertical axis of revolution. And I want you to set up, but not solve, using disc and washer and shell. So you don't have to solve anything, but you do need to set up, including a diagram and your formula. And you don't need to simplify your formula. Like the formulas I have are totally fine. They actually show me very much that you understand what's your big R, what's your little r, or what's your height, what's your radius, okay? So we're gonna stop here. It is 11:23. So if you could finish this setup for C and D, send me that picture by 12:30. That would be excellent.